Cool It by Olivia, an experiment on exponential decay. A decay factor is a rate between 0 and 1 at which the data decreases by. In this experiment, we recorded the temperature of boiled water for 45 minutes every minute. So every minute we took the temperature of the water. So in this experiment, we used hot water, a temperature probe, a mug, and a calculator. Here's a table with the temperatures for every 5 minutes of the boiling water. Now, I'm going to show you how to find the decay factor by using a table. To find the decay factor, use a point. Let's choose point A. So at 0 seconds, the temperature was 87.69 degrees Celsius. And you choose the point before that, or after that, which is B. After 5 minutes, the temperature was 74.95 degrees Celsius. So what we do is we would do 74.95 divided by 87.69, and this would equal 0.85. Now, if I was to continue doing this, I'd get about the same answer. And this might not be the exact same decay factor, but it's close because you can't get the exact one because this data isn't perfectly consistent. So this would equal our decay factor. Now, to find the initial condition, which is the y-intercept, you just look at the temperature where there's no time, and that's your initial condition. So our initial condition is 87.69. Now, I'm going to describe how we found the decay factor using a graph. So basically, it's almost the same thing as using a table. Choose 2 points on the graph. Let's choose A and B again. Now, look at their location, and that might be a bit hard, so you can look over here. And as you can see, it's the 87.69 and 74.95. Now, what you have to do is do the 74.95 divided by 87.69 to get 0.85. See, it's basically the same thing as before. And you could do this with any other 2 points on the graph. You might not get the exact same growth factor, but as long as it's close, that's all really. Decay factor, you might not get the exact same decay factor, but as long as it's close, that's all that's really important. Now we're going to find the initial condition, which, as I said before, is the same as the y-intercept. So basically, it's point A, 87.69, because that's where all the data starts, and that's where when we just started, that's the first temperature we got. Now, I'm going to show you how we found the decay factor using an equation. In an equation, there are 2 parts. The y-intercept, also known as the initial condition, and there is the decay factor. Now, if you want to see what the temperature is at 5 minutes, what you have to do is you have to multiply this answer, so 87.69, and then you multiply it by the decay factor, which isn't the same as all of them, but this is the one that matched the graph, and it was close to it, but you can't get a perfect answer. So you would multiply it by 0.979, and then you say you want to find it to the power of 5, you get it to the power of 5, and then you would get the answer which you want, and that answer is 74.95. Why temperature difference is important. Here's the graph that shows the difference in the room temperature and the water. So basically, the room temperature was 20.3 degrees Celsius, and we found the difference by subtracting the temperature of the water by the room temperature, and you can see those results here. Now, the difference is important because you may ask, when will the water hit room temperature, and you'll find that out because as it's slowly decreasing, it's slowly getting closer to room temperature, and basically when the difference is 0, it means that there's no difference between the temperatures, so the water had hit room temperature. So to summarize what I learned, basically for the graph and the table, you divide point B by point A, or any point before another point, you divide that to get the decay factor. And on the equation, this is the y-intercept, and this is the growth factor, and if you multiply them together to a power of, say, 5, then you'd find out what the temperature was at 5 minutes. And this is how you learn about the decay factor. Thank you for watching. Thanks for watching.